Welcome everyone. Today we are going to do something really special together. We are going to decode poker, not just learn a few facts about it, but actually prove, step by step, exactly why the game works the way it does. And we are going to do it using mathematics. Now, before you worry, you do not need an advanced math degree for any of this. I promise you that. Everything we cover today, we will build up slowly, carefully, and visually. If you have ever been curious about where the odds in poker actually come from, not just what they are, but why they are what they are, then this is exactly the right place to be. Here is the central question we are going to answer together. How many unique 5-card poker hands are possible from a standard deck of cards? The answer is 2,598,960. That is a big number, but by the time we are done today, you are going to understand exactly where every single one of those hands comes from, not just the total, but each category. Each type, each formula. We are going to approach this using a beautiful tool called the 13x4 visual grid. Think of it as a map of the entire deck, laid out so that we can see every card, every rank, and every suit all at once in one clean picture. And once you see the deck that way, the mathematics practically explains itself. Here is the roadmap for everything we will cover. First, we will define our universal set, the complete collection of all 52 cards, and understand exactly how the number 2,598,960 arises from it. Second, we will use the grid method to calculate hands visually using what we call columns for the ranks and rows for the suits. Third, we will discover the 7 master partitions, 7 ways of splitting the number 5 that mathematically describe every possible type of poker hand. Fourth, we will work through what we call set M, the hands with multiplicities, the hands where at least 2 cards share the same rank. These are the 1 pair, 2 pair, 3 of a kind, full house, and 4 of a kind. And fifth, we will work through set D, the hands with distinct ranks, the hands where all 5 cards come from completely different ranks. These include the high card, the straight, the flush, and the straight flush and royal flush. And finally, we will bring everything together into one grand total, with a beautiful logarithmic frequency chart that confirms our mathematics is perfectly correct. So let us begin. Take a breath, settle in, and let us build this together from the very beginning. The first thing we need to do is define our playing field, the standard deck of 52 cards. Now, rather than just listing 52 cards in a long, disorganized column, we are going to lay them out in a way that reveals their mathematical structure immediately. We are going to arrange them as a 13x4 grid. That means 13 columns and 4 rows. Let us talk about the columns first. Each column represents a rank. There are 13 ranks in a standard deck. Starting from the left, we have the ace, then 2, then 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. So we have 13 columns, 1 for each rank, reading left to right across the top of the grid. Now let us talk about the rows. Each row represents a suit. There are 4 suits in a standard deck. Reading from top to bottom, we have spades, hearts, diamonds, and clubs. So we have 4 rows, 1 for each suit, running down the left side of the grid. Now here is the beautiful part. Every single card in the deck lives at the intersection of 1 column and 1 row. The card at the intersection of the ace column and the spades row is the ace of spades. The card at the intersection of the king column and the clubs row is the king of clubs. Every card has exactly 1 rank and exactly 1 suit, which means every card occupies exactly 1 unique cell in this grid. No overlaps, no duplicates, no gaps. So when you look at this grid in its entirety, you are looking at all 52 cards, perfectly organized. 13 columns across, 4 rows down. 13 times 4 equals 52. Every card accounted for. This grid is not just a pretty picture. It is the foundation for every calculation we are going to make for the rest of this video. The columns, the ranks, will tell us which ranks appear in a hand. The rows, the suits, will tell us which suits appear. And by choosing columns and rows together, we can describe any poker hand mathematically. Now that we have our 52 cards laid out in the grid, the next question is, what exactly is a poker hand? A poker hand is a group of exactly 5 cards chosen from the deck. In mathematical language, it is a subset of exactly 5 elements selected from our set of 52. And a very important word here is subset, because order does not matter. We are not arranging the 5 cards in a sequence. We are simply choosing a group of 5. The hand containing the ace of spades, jack of hearts, 8 of diamonds, 5 of clubs, and king of spades is the same hand no matter what order you pick those cards up from the table. So the question becomes, How many ways can we choose 5 cards from 52 when order does not matter? This is where our choose formula comes in. In spoken terms, 52 choose 5. And the way we calculate that is 52 factorial divided by the product of 5 factorial and 47 factorial. Let me explain what that means in plain English. 52 factorial means 52 times 51 times 50 times 49 times 48, and so on all the way down to 1. That is the number of ways to arrange all 52 cards in a sequence. But since we only want groups of 5, where order does not matter, we divide by the number of ways to rearrange 5 items among themselves, which is 5 factorial, meaning 5 times 4 times 3 times 2 times 1. And we also divide by 47 factorial to account for all the remaining cards we did not choose. When you work through all of that arithmetic, you arrive at exactly 2,598,960. That is the size of our universe. There are exactly 2,598,960 distinct 5-card hands possible from a standard 52-card deck. To make this concrete, here is an example of one such hand highlighted on the grid. We have the Ace of Spades, the Jack of Hearts, the 8 of Diamonds, the 5 of Clubs, and the King of Spades. 5 cards. 5 cells highlighted in the grid. That is one hand out of nearly 2.5 million possibilities. Every single one of those 2,598,960 visual patterns, each unique way of lighting up exactly 5 cells in our 13x4 grid, is a distinct poker hand. So now we know how many hands there are. But how do we calculate the number of hands in each specific category? How do we figure out exactly how many full houses exist? Or how many flushes? Or how many one pairs? This is where the grid becomes an incredibly powerful calculating tool. The key idea is that we can apply the choose formula directly to the dimensions of the grid itself. Let me explain exactly what I mean. Remember, our grid has 2 dimensions. It has columns, the ranks, and it has rows, the suits. And when we want to count hands of a certain type, we make 2 separate choices. We choose which columns to use, and then we choose which rows to fill within each of those columns. Let us look at the column choice first. We have 13 columns, 13 ranks running across the top. If we want to choose some number of them, say we want to choose exactly 2 ranks, we use the phrase 13 choose 2. That means, out of 13 available columns, in how many ways can I select exactly 2 of them where order does not matter? As a concrete example, 13 choose 2 includes the selection of the king column and the 10 column. It includes aces and 5s. It includes 7s and queens. Every possible pair of columns. Now, once we have selected a column, we need to decide which specific cards within that column to include. Each column has 4 cells, 1 for each suit, 1 for spades, 1 for hearts, 1 for diamonds, 1 for clubs. If we want to include, say, exactly 2 of those 4 cells, we use the phrase 4 choose 2. That means, out of 4 available suit boxes in that column, in how many ways can I select exactly 2? So the general pattern for any hand type is, choose some columns from the 13 available, and then within each chosen column, choose some rows from the 4 available. Multiply those choices together, and you get the count for that type of hand. For instance, 13 choose 2 means picking exactly 2 separate columns, like selecting kings and 10s as your 2 ranks. And 4 choose 2 means filling exactly 2 of the 4 suit boxes inside a chosen column, like taking the spade and the heart versions of a card, but not the diamond or the club. This column and row logic is the engine behind every single calculation we are going to make. Different hand types will require different column patterns and different row selections, but the underlying principle is always the same. Choose your columns, choose your rows, multiply. Now we arrive at what I think is one of the most elegant ideas in this entire journey. We have nearly 2.5 million hands to organize. How do we make sure we count every single type without missing anything and without counting anything twice? The answer is, we use a mathematical technique called partitioning the integer 5. Here is what I mean. Every 5-card hand uses exactly 5 cards. Those 5 cards are distributed across some number of ranks, some number of columns in our grid. And the pattern of how those 5 cards are spread across the columns defines the type of hand. Think about a 4-of-a-kind hand. 4 of the 5 cards share the same rank. They all go in the same column. The 5th card is from a different rank. It goes in a different column. So the distribution of cards across columns is 4 in one column and 1 in another. We write that as the group 4 plus 1. Think about a full house. 3 cards share one rank, and 2 cards share another rank. So the distribution is 3 in one column, 2 in another column. We write that as 3 plus 2. Think about a one-pair hand. 2 cards share the same rank, and the other 3 cards are all from different ranks. So the distribution is 2 in one column, then 1 in a third column, 1 in a fourth column, and 1 in a fifth column. We write that as 2 plus 1 plus 1 plus 1. And think about a high card hand, where no 2 cards share the same rank at all. All 5 cards are in completely different columns. The distribution is 1 in one column, 1 in a second, 1 in a third, 1 in a fourth, and 1 in a fifth. We write that as 1 plus 1 plus 1 plus 1 plus 1. This is the partition of 5. It is the complete list of all the ways you can write the number 5 as a sum of positive whole numbers. And it turns out there are exactly 7 such ways. Let me go through all 7. The first is just the number 5 by itself, written as a group containing only the number 5. This means 5 cards all sharing the same rank, which would be a 5-of-a-kind hand. But we will see in a moment why this is impossible in a standard deck. The second is 4 plus 1. 4 cards sharing one rank, and 1 card of a different rank. This is 4 of a kind. The third is 3 plus 2. 3 cards of one rank, 2 cards of another rank. This is a full house. The fourth is 3 plus 1 plus 1. 3 cards of one rank, and then 2 individual cards each from their own unique rank. This is 3 of a kind. The fifth is 2 plus 2 plus 1. 2 cards of one rank, 2 cards of another rank, and 1 card from a third distinct rank. This is 2 pair. The sixth is 2 plus 1 plus 1 plus 1. 2 cards sharing a rank, and then 3 more cards each from their own separate rank. This is 1 pair. And the seventh is 1 plus 1 plus 1 plus 1 plus 1, 5 ones, meaning all 5 cards come from 5 completely different ranks. This is the category that contains our high card hands, straights, flushes, and straight flushes. These 7 integer partitions are exhaustive and mutually exclusive. That means together they cover every possible poker hand, and no hand belongs to more than one category. They are our 7 master partitions, and they will guide everything that comes next. Now we have just finished building our complete map of the integer partitions of 5. We have 7 unique ways to write 5 as an ordered sum of positive integers. And each one of those partitions describes a distinct family of poker hands. But before we dive into calculating each family one by one, I want to take a moment to step back and organize everything neatly into 2 big groups. Think of it as sorting your tools before you begin a project. We are going to call these 2 groups our 2 master sets. And once you understand the difference between them, all of the calculations that follow will feel completely natural. The first group is called Set M. The M stands for Multiplicities. This group contains all of the integer partitions from 1 through 6. In other words, any hand where at least one rank appears more than once. In the language of our grid, these are all the hands where at least one vertical column has 2 or more dots placed inside it. So a hand with 3 kings and 2 fives falls into Set M. A hand with 4 jacks and 1 stray card falls into Set M. Anytime you see a column with multiple dots, you are in Set M. The second group is called Set D. The D stands for distinct ranks. This group contains only the 7th partition, the one that looks like 1 plus 1 plus 1 plus 1 plus 1. In this family, every single card in the hand comes from a completely different rank. No column is ever touched more than once. Every dot lives in its own unique vertical column. Hands like straights, flushes, and high card hands all belong to Set D. This split is not arbitrary. It is mathematically motivated. The reason we separate these 2 families is that they each require a fundamentally different counting strategy. Set M hands have repeated ranks, which means we have to be careful about how we handle symmetry and avoid overcounting. Set D hands are all distinct, which opens the door to a different kind of combinatorial reasoning involving sequential and uniform conditions. So keep this division in mind as we move forward. Set M on one side, with multiplicities. Set D on the other, with all distinct ranks. Together, they cover every single possible poker hand. No overlaps, no gaps. Let us now begin working through Set M, one partition at a time. We start with the very first partition, which is simply the number 5 on its own, written as a single group of 5. In terms of our grid, this means we are placing all 5 dots inside one single vertical column. Think about what that would look like. You pick one rank, say the rank of queens, and you want 5 cards, all of that same rank. So in the grid, you move to the queen column, and you start filling in boxes. The queen of spades, the queen of hearts, the queen of diamonds, the queen of clubs. And now you need a 5th box. But look at the column. It has exactly 4 boxes. One for each suit. You have already filled all of them, and you still need one more. There is simply no 5th box to fill. This is not a close call. This is not a matter of searching harder or being creative. The column ends at 4. It always ends at 4 for every single rank in the deck. That is because there are exactly 4 suits: spades, hearts, diamonds, and clubs, and nothing more. Now, I said this is impossible, but let me show you 3 examples just so we can truly feel the problem, and then we will confirm it with the math. Imagine trying to make 5 of a kind with 7s. You would need the 7 of spades, the 7 of hearts, the 7 of diamonds, the 7 of clubs, and a 5th 7 that simply does not exist in the deck. The column is full, and there is no 5th row. Imagine trying to do it with aces. Ace of spades, ace of hearts, ace of diamonds, ace of clubs, and again, you need one more ace. But the deck gives you exactly 4 aces, and no more. Try it with 9s. Same result. 4 boxes, 4 suits, 4 cards. The 5th card you need is not there. No matter which rank you choose, the story is the same. The column runs out before you reach 5. Now let us see how the mathematics captures this perfectly. We write the formula as 13 choose 1, multiplied by 4 choose 5. The first part, 13 choose 1, is straightforward. We are choosing one column from the 13 available ranks. That is fine. 13 columns are available, and we pick one. But the second part is where everything collapses. 4 choose 5 is asking us to select 5 items from a group that only contains 4. In combinatorics, this is simply not allowed. When the number you want to choose exceeds the number available, the result is 0. There are 0 ways to do it. Not one way. Not a small number. Exactly 0. So the full calculation is 13 multiplied by 0, which is 0. The total number of 5-of-a-kind combinations in a standard deck is exactly 0. This hand is impossible. And now you understand exactly why. Not as a rule someone told you, but as a mathematical certainty built directly into the structure of the deck. We now move to the second partition, which we write as 4 plus 1. This is the 4-of-a-kind hand. In the grid, this hand splits neatly into 2 groups. The first group has 4 dots, and they all go into one column. The second group has a single dot, and it goes into a completely separate column. So when you look at the grid for a 4-of-a-kind hand, you see one column that is entirely full, all 4 of its boxes highlighted. And then somewhere else, in a different column, there is one isolated dot sitting in just one of the 4 boxes. That lone card, sitting in the second column, is what poker players call the kicker. It plays no matching role. It is simply along for the ride. Let us bring this to life with our 3 examples before we touch the formula. The first example is 4 7s with a 2 of diamonds as the kicker. In the grid, look at the column for the rank of 7. All 4 boxes are highlighted: the 7 of spades, the 7 of hearts, the 7 of diamonds, and the 7 of clubs. The entire column is full. Then, in the column for the rank of 2, a single box is highlighted, specifically the row for diamonds. That one dot in that one box of that second column is your kicker card. The second example is 4 aces with a king of spades as the kicker. The ace column is completely filled: ace of spades, ace of hearts, ace of diamonds, ace of clubs. And in the king column, one box is highlighted, the spades row. One full column, one isolated dot. The third example is 4 9s with a 5 of hearts as the kicker. The 9 column is entirely highlighted across all 4 suits. And in the 5 column, one box is marked the hearts row. Every 4-of-a-kind hand looks exactly like this in the grid. One column completely saturated, and one independent dot elsewhere. Now let us build the formula and count exactly how many of these hands exist. We handle the 2 groups separately and then multiply. For the first group, the 4-of-a-kind part, we need to choose which column will be completely filled. We have 13 ranks, so we write 13 choose 1. Then, within that chosen column, we need to fill all 4 boxes. Since we want all 4 of the 4 available boxes, we write 4 choose 4. And 4 choose 4 is always equal to 1. There is only one way to select every item from a group, which is simply to take all of them. So the first part gives us 13 multiplied by 1, which is 13. For the second group, the kicker, we have already used one column. That leaves 12 columns remaining. We choose one of them, so we write 12 choose 1. Then within that column, we pick one of its 4 boxes. One suit for our kicker, so we write 4 choose 1, which equals 4. The second part gives us 12 multiplied by 4, which is 48. Multiplying both parts together, we get 13 multiplied by 48, which equals 624. There are exactly 624 four-of-a-kind hands in a standard deck of 52 cards. We now move to the third partition, which we write as 3 plus 2. This is the full house. In the grid, this hand activates exactly 2 columns. The first column has 3 of its 4 boxes filled, 3 suits chosen from 4 for the three-of-a-kind rank. The second column has exactly 2 of its 4 boxes filled, 2 suits chosen from 4 for the pair rank. 3 dots in one column, 2 dots in another. That visual pattern, a taller group and a shorter group side by side, is the fingerprint of the full house in our grid. Let us explore this with 3 examples before we calculate. The first example is called Jacks full of 4s. That name tells you exactly what to look for in the grid. The Jack column has 3 boxes highlighted: the Jack of Spades, the Jack of Hearts, and the Jack of Diamonds. 3 suits, 3 dots, and the 4 column has 2 boxes highlighted: the 4 of Hearts and the 4 of Clubs. 2 suits, 2 dots. Notice the naming convention in poker. The three-of-a-kind rank always comes first. You say the rank that appears 3 times, then the word full of, and then the rank that appears twice. So Jacks full of 4s means 3 Jacks and 2 4s, not the other way around. The second example is Aces full of Kings. The Ace column shows 3 highlighted boxes: the Ace of Hearts, the Ace of Diamonds, and the Ace of Clubs. The King column shows 2 highlighted boxes: the King of Spades and the King of Hearts. The third example is Eights full of 2s. The 8 column has 3 boxes filled: the 8 of Spades, the 8 of Diamonds, and the 8 of Clubs. The 2 column has 2 boxes filled: the 2 of Spades and the 2 of Diamonds. In every case, the structure is the same. The taller column of 3 is the trips, and the shorter column of 2 is the pair. Now let us derive the count. We handle the 2 groups separately and then multiply. For the first group, the three-of-a-kind column, we choose 1 rank from 13. That is 13, choose 1. Then within that column, we choose 3 boxes from the 4 available. That is 4, choose 3. Now, 4 choose 3 equals 4, because there are exactly 4 ways to leave out 1 box from a group of 4. Whichever suit you exclude, the other 3 are chosen. So the first part is 13 multiplied by 4, which equals 52. For the second group, the pair column, we have already used 1 column, leaving 12. We choose 1 of them, so we write 12, choose 1. Within that column, we choose 2 boxes from 4, so we write 4, choose 2. 4, choose 2 equals 6, because there are 6 ways to pick 2 items from a group of 4. The second part is 12 multiplied by 6, which equals 72. Multiplying both parts together, we get 52 multiplied by 72, which equals 3,744. There are exactly 3,744 full house hands in the deck. We now arrive at the fourth partition, which we write as 3 plus 1 plus 1. This is the three-of-a-kind hand. In the grid, this hand uses 3 separate columns. The first column has 3 of its 4 boxes filled. That is the three-of-a-kind rank. The second column has exactly 1 box filled. The third column also has exactly 1 box filled. So you have 1 column with a group of 3 dots, and then 2 separate columns each carrying a single lone dot. Those 2 single dot columns are the kicker cards, the extra cards that round out the hand without contributing to any matching pattern. Let us look at our 3 examples before we calculate, so you can see this pattern clearly. The first example is Trip Queens with a 7 of clubs and a 2 of spades as kickers. In the grid, the Queen column has 3 boxes highlighted: the Queen of Spades, the Queen of Hearts, and the Queen of Diamonds. Then the 7 column has 1 box highlighted, the Clubs row, and the 2 column has 1 box highlighted, the Spades row. 1 group of 3 and 2 isolated singles. The second example is Trip 5s with a Jack of Spades and a 9 of Hearts. The 5 column shows 3 highlighted boxes: the 5 of Hearts, the 5 of Diamonds, and the 5 of Clubs. The Jack column shows 1 box, the Spades row, and the 9 column shows 1 box, the Hearts row. The third example is Trip Aces, with a King of Hearts and a Queen of Diamonds. The Ace column has 3 boxes lit up: the Ace of Spades, the Ace of Diamonds, and the Ace of Clubs. The King column has 1 box highlighted, the Hearts row. The Queen column has 1 box highlighted, the Diamonds row. The pattern is consistent across all 3. 1 tall column and 2 quiet single dot columns standing apart from it. Now let us build the formula, and there is one subtle but very important point here that I want you to pay close attention to, because it is easy to get wrong. For the three-of-a-kind column, we choose 1 rank from 13. 13 choose 1, and then we choose 3 boxes from 4 within that column. 4 choose 3, which equals 4. That gives us 13 multiplied by 4, which is 52. Now for the two kicker columns, here is where we must be careful. Both kicker columns belong to exactly the same partition group. Both have a partition size of 1. They play identical structural roles in the hand. Because of this, the two kickers are interchangeable. There is no first kicker and second kicker. They are just two columns of the same type. If we were to choose them one at a time, first pick one column, then pick another column from what remains, we would end up counting the same pair of columns twice. Choosing 7 first and then Jack would be counted separately from choosing Jack first and then 7. But 7 and Jack together, in whatever order we chose them, represent the exact same hand. That would be overcounting. The correct approach is to choose both kicker columns simultaneously as a single pair. We use 12 choose 2. 12 because one column is already taken by the trips, and choose 2 because we want both kickers at once, treating them as a set rather than a sequence. 12 choose 2 equals 66. Then for each of those two kicker columns, we pick one of the 4 boxes, one suit per column. That is 4 choose 1, raised to the power of 2. 4 choose 1 is 4, and 4 squared is 16. Putting it all together, 52 multiplied by 66 multiplied by 16. 52 times 66 is 3,432. And 3,432 multiplied by 16 gives us 54,912. There are exactly 54,912 three-of-a-kind hands in the deck. We now come to the fifth partition, which we write as 2 plus 2 plus 1. This is the two-pair hand. In the grid, this hand lights up 3 separate columns. 2 of those columns each have exactly 2 of their 4 boxes filled, and the third column has just 1 box filled. So when you look at the grid, you see 2 columns that each carry a small pair of dots, and 1 column standing apart from both of them with a single lone dot. 2 columns of height 2, and 1 column of height 1. The 2 matching columns are your 2 pairs, and the single dot column is your kicker. Let us look at 3 examples to make this visual pattern completely clear. The first example is 10s and 8s with a 4 of spades as the kicker. In the grid, the 10 column has 2 boxes highlighted, the 10 of spades and the 10 of hearts. The 8 column also has 2 boxes highlighted, the 8 of diamonds and the 8 of clubs. And then the 4 column has 1 box highlighted, the spades row. 2 pairs sitting in their columns, and 1 quiet kicker beside them. The second example is aces and kings, with a 2 of hearts as the kicker. The ace column shows 2 highlighted boxes, the ace of spades and the ace of hearts. The king column shows 2 highlighted boxes, the king of diamonds and the king of clubs. And the 2 column shows 1 highlighted box, the hearts row. The third example is 5s and 3s with an ace of diamonds as the kicker. The 5 column has 2 boxes lit, the 5 of hearts and the 5 of clubs. The 3 column has 2 boxes lit, the 3 of spades and the 3 of hearts. And the ace column has 1 box lit, the diamonds row. In every case, the visual fingerprint is the same. 2 equally sized columns of 2 and 1 standalone column of 1. Now let us build the formula, and once again there is a critical point about symmetry that we must handle correctly. For the 2 pair columns, notice that both of them belong to the same partition group. Both have a partition size of 2. They are structurally identical. Neither pair is the first pair, and neither is the second pair. They are simply 2 columns of the same type, and they are interchangeable. This means, just as we saw with the kicker columns in 3 of a kind, we must choose both pair columns simultaneously rather than one at a time. We use 13 choose 2, selecting both pair columns at once from all 13 available ranks. 13 choose 2 equals 78. Then within each of those 2 columns we choose 2 boxes from the 4 available. That is 4 choose 2, which equals 6, applied to each column. Because both columns are chosen at the same time and treated identically, we raise this to the power of 2. 6 squared equals 36. So the combined contribution from the 2 pair columns is 78 multiplied by 36, which equals 2,808. Now for the kicker column. We have already used 2 columns for our pairs, leaving 11 columns to choose from. We pick one of them. 11 choose 1, which is 11. Within that column, we pick one of the 4 boxes. 4 choose 1, which is 4. So the kicker contributes 11 multiplied by 4, which equals 44. Multiplying everything together, 2,808 multiplied by 44 gives us 123,552. There are exactly 123,552 two-pair hands in a standard deck. We now arrive at the 6th and final partition in set M. We write it as 2 plus 1 plus 1 plus 1. This is the one-pair hand. In the grid, this hand uses 4 separate columns. One column has exactly 2 of its 4 boxes filled. That is the pair. Each of the remaining 3 columns has exactly 1 box filled. So what you see in the grid is one column with a pair of dots, and then 3 separate columns each carrying a single isolated dot. One column of 2 and 3 columns of 1. Those 3 single dot columns are all kicker cards. Let us ground this with our 3 examples. The first example is a pair of 6s with kickers King of Diamonds, 9 of Clubs, and 5 of Spades. In the grid, the 6 column has 2 boxes highlighted, the 6 of Spades and the 6 of Hearts. Then 3 separate columns each carry a single dot. The Diamonds row of the King column, the Clubs row of the 9 column, and the Spades row of the 5 column. One pair, 3 kickers. The second example is a pair of aces with kickers Queen of Clubs, Jack of Spades, and 4 of Hearts. The ace column shows 2 boxes, the Ace of Hearts and the Ace of Diamonds. Then the Queen column has the Clubs row highlighted, the Jack column has the Spades row highlighted, and the 4 column has the Hearts row highlighted. The third example is a pair of 2s with kickers 8 of Hearts, 7 of Diamonds, and 3 of Spades. The 2 column has 2 boxes highlighted, the 2 of Spades and the 2 of Clubs, and 3 individual columns carry 1 dot each, Hearts in the 8 column, Diamonds in the 7 column, and Spades in the 3 column. In every one-pair hand, the grid tells the same story. One column with a pair of dots standing slightly taller, surrounded by 3 solitary dots in 3 separate columns. Now let us calculate, and once again the question of symmetry is crucial. For the pair column, we choose 1 rank from 13. 13 choose 1. Then we choose 2 boxes from 4 within that column. 4 choose 2, which equals 6. The pair part contributes 13 multiplied by 6, which equals 78. Now for the 3 kicker columns. All 3 of them belong to the same partition group. Each has a partition size of 1. All 3 are structurally identical and completely interchangeable. There is no ordering among them, so we must choose all 3 kicker columns simultaneously as a group. We have already used 1 column for the pair, leaving 12. We choose 3 columns at once from those 12. 12 choose 3. 12 choose 3 equals 220. Then within each of those 3 kicker columns, we pick 1 box from 4. 4 choose 1 for each, which is 4. Since we treat all 3 columns simultaneously, we raise 4 to the power of 3. 4 cubed is 64. The kicker part contributes 220 multiplied by 64, which equals 14,080. Now we multiply the pair part by the kicker part. 78 multiplied by 14,080 gives us 1,098,240. There are exactly 1,098,241 pair hands in the deck. That is a strikingly large number, far larger than any other set M hand. And it makes intuitive sense. The one-pair hand is the most flexible, the most loosely constrained. You only need 2 cards to match, and the other 3 can be almost anything. That enormous freedom to combine translates directly into an enormous count. And with that, we have completely finished set M. Every partition from 1 through 6 has been accounted for. 5 of a kind at 0, 4 of a kind at 624, full house at 3,744, 3 of a kind at 54,912, 2 pair at 123,552, and 1 pair at 1,098,240. Each one derived from first principles, step by step, using nothing more than our grid and the language of combinations. Now we turn our attention to set D, the family of distinct ranks. This is the 7th and final partition, written as 1 plus 1 plus 1 plus 1 plus 1. Every dot in its own unique column. No column is ever shared. No rank ever repeats. In the grid, a set D hand always highlights exactly 5 separate columns, with 1 dot in each. The 5 dots are scattered across the grid, sometimes in the same row, sometimes in different rows, but always in 5 completely different columns. The starting point for everything in set D is what we can call the baseline formula. We choose 5 distinct columns from the 13 available. That is, 13 choose 5. 13 choose 5 equals 1,287. Then, for each of those 5 columns, we pick one of the 4 available boxes. That is, 4 choose 1, applied 5 times, which means 4 raised to the power of 5. 4 to the 5th power equals 1,024. Multiplying these together, 1,287 multiplied by 1,024 equals 1,317,888. That is the baseline. the total number of hands with 5 distinct ranks before we apply any further conditions. But within set D, the hands are not all the same. They differ based on 2 specific conditions that we can impose on the 5 chosen columns and their dots. The first condition is about whether the 5 columns are sequential. That is, whether the ranks form a consecutive run like 5, 6, 7, 8, 9, or 10, Jack, Queen, King, Ace. Sequential columns form what poker players call a straight. The second condition is about whether all 5 dots land in the same row, meaning all 5 cards share the exact same suit. When all dots are in the same horizontal row, we have what poker players call a flush. These 2 conditions can each be present or absent, and the combination of whether each condition is met or not is precisely what separates the 4 distinct hand types within set D. Straight flushes meet both conditions. Flushes meet only the suit condition. Straights meet only the sequence condition. And high card hands meet neither. We will work through each of these carefully, one by one. Let us begin with the hand that satisfies both conditions at once. The columns are sequential, and all the dots sit in the same row. This is the straight flush, and specifically now we are going to look at its rarest and most celebrated form, the royal flush. In the grid, a royal flush is visually unmistakable. 5 consecutive columns from 10 through ace, that is, the 10 column, the jack column, the queen column, the king column, and the ace column. All 5 dots sit in the exact same horizontal row, meaning all 5 cards share the same suit. The entire hand is perfectly flat across one row, occupying exactly those 5 consecutive columns. And here is what makes the royal flush so special among all straight flushes. There is exactly one sequence of 5 consecutive columns that spans from 10 to ace. Only one. You cannot slide it left or right. 10, Jack, Queen, King, Ace. Those are the 5 highest ranks in the deck, and there is no other set of 5 consecutive ranks that ends at ace and begins at 10. That sequence is unique and fixed. Let us look at all 4 possible royal flushes, because there are exactly 4, one for each suit. The first is the royal flush of spades. All 5 dots sit in the spades row, the top row of the grid. We see the ace of spades, the 10 of spades, the jack of spades, the queen of spades, and the king of spades, all highlighted, flat across the very top of the grid. The second is the royal flush of hearts. All 5 dots sit in the hearts row, the second row. Ace of hearts, 10 of hearts, jack of hearts, queen of hearts, king of hearts. The third is the royal flush of diamonds. All 5 dots sit in the diamonds row, the third row. Ace of diamonds, 10 of diamonds, jack of diamonds, queen of diamonds, king of diamonds. The fourth is the royal flush of clubs. All 5 dots sit in the clubs row, the bottom row of the grid. Ace of clubs, 10 of clubs, jack of clubs, queen of clubs, king of clubs. 4 hands. 1 per suit. That is all. Now the formula reflects this simplicity beautifully. We write it as 1, multiplied by 4, choose 1. The 1 captures the fact that there is exactly one valid sequence of columns that qualifies as a royal sequence, the sequence from 10 to ace. Just 1. No choices to make, no decisions about which columns to use. They are fixed. Then 4 choose 1 captures the choice of suit. Which of the 4 rows will all 5 dots land in? 4 choose 1 equals 4. 1 multiplied by 4 is 4. The total number of royal flush hands is exactly 4. The 4 rarest hands in all of poker, and now you can see precisely why. There is one sequence, 4 suits, and nothing more. Now we stay within the straight flush family, but we step down from the royal and consider all the other straight flushes. The ones where the 5 sequential columns form a consecutive run that is not the 10 through ace sequence. In the grid, these hands look identical in structure to the royal flush. All 5 dots sit in the same horizontal row, and the 5 highlighted columns form a consecutive run. The only difference is that the sequence does not end at ace. It might end at king, or at queen, or all the way down at 5. And it turns out there are exactly 9 other sequences of 5 consecutive columns that we can form. Let us think about why. The lowest possible straight flush sequence uses ace, 2, 3, 4, 5, with the ace playing the role of a low card. That is the 5 high sequence. From there, the window slides upward, 2 through 6 for 6 high, 3 through 7 for 7 high, all the way up to 9 through king for king high. That king high sequence is the highest non-royal straight flush. And the next step up, 10 through ace, is the royal, which we already counted separately. So we have 10 high through king high, plus the special case of 5 high with the low ace. Count them. 5 high, 6 high, 7 high, 8 high, 9 high, 10 high, Jack high, Queen high, King high. That is 9 sequences. Let us look at 3 examples before we confirm the count. The first example is the 5 high straight flush of clubs. All 5 dots sit in the clubs row, the bottom row of the grid. The highlighted columns are ace, 2, 3, 4, and 5, with the ace serving here as the lowest card, not the highest. The dots stretch from the very first column across to the 5 column, all flat along the bottom row. The second example is the 9 high straight flush of hearts. All 5 dots sit in the hearts row. The highlighted columns are 5, 6, 7, 8, and 9. 5 consecutive columns sitting in the middle of the grid, all in the second row. The third example is the king high straight flush of spades. All 5 dots are in the spades row, the top row. The highlighted columns are 9, 10, Jack, Queen, and King. This is the highest non-royal sequence, ending 1 step below the ace. Every non-royal straight flush follows the same visual pattern. 5 consecutive columns, perfectly flat in 1 row, with the sequence stopping short of the royal 10 through ace window. Now for the formula. We write it as 9 multiplied by 4, choose 1. The 9 counts the number of valid non-royal sequences of 5 consecutive columns. We established there are 10 total sequential windows in a 13-rank deck, and we subtract the 1 royal sequence, leaving 9. Then 4 choose 1 counts the choice of suit, which row all 5 dots will sit in. 4 choose 1 is 4. 9 multiplied by 4 equals 36. There are exactly 36 non-royal straight flush hands in the deck. Adding the 4 royal flushes, the total number of all straight flush hands, royal and non-royal combined, is 40. 40 hands out of 2,598,960. Those are extraordinarily rare odds, and now you know exactly where that rarity comes from. The grid constrains you to a single row and a single fixed window of consecutive columns. There is almost nowhere to go. We just established that there are 36 non-royal straight flush hands in the deck, 9 sequences, each available in 4 suits. And I think it is worth pausing here to actually see all 36 of them. Not just a handful of examples, but every single one laid out in front of us. Because when you see the complete picture, the mathematics stops being abstract. Each of these 36 hands is a real holdable thing. 5 specific cards that could actually land in your hand across a table. We are going to walk through them suit by suit. First, all 9 spades straight flushes, then all 9 hearts, then all 9 diamonds, and finally, all 9 clubs. By the time we are done, we will have accounted for every last one. Let us begin with spades. In every spades straight flush, all 5 dots sit in the very top row of the grid, the spades row. The row never changes. What changes from hand to hand is which 5 consecutive columns are highlighted. The first hand is the 5 high straight flush of spades. The highlighted columns are ace, 2, 3, 4, and 5, all in the spades row. The ace is playing its low role here, anchoring the bottom of the sequence. So the 5 cards are the ace of spades, the 2 of spades, the 3 of spades, the 4 of spades, and the 5 of spades. The second hand is the 6 high straight flush of spades. The window slides 1 step to the right. The highlighted columns are now 2, 3, 4, 5, and 6, all spades. The ace is gone, and the 6 has entered at the top. 2 of spades, 3 of spades, 4 of spades, 5 of spades, 6 of spades. The third hand is the 7 high straight flush of spades. 1 more step to the right. Columns 3, 4, 5, 6, and 7, all in the spades row. 3 of spades, 4 of spades, 5 of spades, 6 of spades, 7 of spades. The fourth hand is the 8 high straight flush of spades. Columns 4, 5, 6, 7, and 8, all spades. 4 of spades, 5 of spades, 6 of spades, 7 of spades, 8 of spades. The fifth hand is the 9 high straight flush of spades. Columns 5, 6, 7, 8, and 9, all in the spades row. 5 of spades, 6 of spades, 7 of spades, 8 of spades, 9 of spades. The sixth hand is the 10 high straight flush of spades. Columns 6, 7, 8, 9, and 10, all spades. 6 of spades, 7 of spades, 8 of spades, 9 of spades, 10 of spades. The seventh hand is the jack high straight flush of spades. Columns 7, 8, 9, 10, and jack, all in the spades row. 7 of spades, 8 of spades, 9 of spades, 10 of spades, jack of spades. The eighth hand is the queen high straight flush of spades. Columns 8, 9, 10, Jack, and Queen, all spades. 8 of spades, 9 of spades, 10 of spades, Jack of spades, Queen of spades. And the ninth and final spades, straight flush, is the king-high straight flush of spades. Columns 9, 10, Jack, Queen, and King, all in the spades row. 9 of spades, 10 of spades, Jack of spades, Queen of spades, King of spades. That is all 9 spades straight flushes. Notice how the window slides steadily to the right, one column at a time, from the ace-low 5-high all the way up to the king-high. The row stays fixed, and the column window travels. Similarly, we have 9 for hearts, 9 for diamonds, 9 for clubs. And there we have it. 9 spades, 9 hearts, 9 diamonds, 9 clubs, 36 non-royal straight flushes, every single one of them displayed in full. Each one is a unique, verifiable hand. No two are the same, and together with the 4 royal flushes, they account for every straight flush that can exist in a standard deck of 52 cards, all 40 of them. Now we move forward to the next hand type within set D. We have handled the case where both conditions are met, sequential columns and a uniform row. Now we look at the case where only the second condition is met, without the first. That is, the 5 dots all sit in the same row, but the 5 columns are not consecutive. This hand is the flush. In the grid, a flush is immediately recognizable. All 5 dots are perfectly flat, sitting in one single horizontal row. You look at the grid and you see 5 highlighted boxes all at the same vertical level, all sharing the same suit. But unlike a straight flush, if you look at which columns those boxes are in, they do not form a consecutive run. They are scattered. They might be spread far apart or clustered in some non-sequential pattern, but they definitely do not march in order from one column to the next. So the defining visual feature of a flush is 1 row, 5 non-consecutive columns. The row is uniform, but the columns are irregular. Let us look at 3 examples to feel this clearly. The first example is an ace-high flush of hearts. All 5 dots sit in the hearts row, the second row of the grid. The highlighted columns are ace, jack, 8, 5, and 2. Look at those column choices. Ace, jack, 8, 5, 2. They are not consecutive. There are gaps between them, but they all sit perfectly flat in the hearts row. 5 hearts, 5 different ranks, no sequential pattern. The second example is a king-high flush of spades. All 5 dots sit in the spades row, the top row of the grid. The highlighted columns are king, queen, 9, 6, and 4. Again, not consecutive. Queen is next to king, but then there is a jump to 9, another jump to 6, and another to 4. All 5 dots are perfectly flat across the top row, but the columns are scattered. The third example is a jack-high flush of diamonds. All 5 dots sit in the diamonds row, the third row of the grid. The highlighted columns are jack, 7, 5, 3, and 2. Not consecutive, but all in the same diamonds row. Jack of diamonds, 7 of diamonds, 5 of diamonds, 3 of diamonds, 2 of diamonds. In every flush, the row is perfectly uniform. 1 suit, 5 cards, but the columns refuse to line up in order. That scattered quality of the columns is precisely what separates a flush from a straight flush. Now let us derive the count carefully, because this is where we use a technique called subtraction, and it is elegant. We write the formula as 4 choose 1, multiplied by the quantity 13 choose 5 minus 10. Let us unpack each piece. 4 choose 1 is the choice of row. Which single suit will all 5 cards belong to? There are 4 suits, and we want exactly one of them. 4 choose 1 equals 4. 13 choose 5 is the number of ways to choose any 5 columns from the 13 available ranks with no restrictions. 13 choose 5 equals 1,287. This counts every possible set of 5 distinct columns, consecutive or not. But here is the problem. Some of those 1,287 combinations of 5 columns happen to be consecutive. Specifically, there are exactly 10 sequential windows of 5 consecutive columns in a 13-rank deck. And if all 5 dots land in the same row and the 5 columns are sequential, that is a straight flush, not a flush. We have already counted those separately, and we must not count them again here. So we subtract those 10 sequential combinations from our column count. 1,287 minus 10 equals 1,277. Now we multiply by the suit choice. 4 multiplied by 1,277 equals 5,108. There are exactly 5,108 flush hands in the deck. Notice the logic of what we just did. We started with all possible 5-column combinations, removed the ones that would accidentally form a straight flush, and then multiplied by the 4 suit choices. The subtraction is the key move. It ensures our flush count and our straight flush count are cleanly separated with no overlap between them. We have now handled 2 of the 4 cases within set D. We counted the hands where both conditions are met, the straight flush. We counted the hands where only the suit condition is met, the flush. Now we turn to the case where only the sequence condition is met, without the suit condition. That is, the 5 columns are consecutive, but the 5 dots do not all sit in the same row. This hand is the straight. In the grid, a straight has a very distinctive look. The 5 highlighted columns are always consecutive. They march in order from one rank to the next without any gaps. But when you look at which row each dot sits in, the dots are jumping around. One dot might be in the spades row, the next in the clubs row, the next in the hearts row, and so on. The columns are locked into a sequential window, but the rows are free to vary. The hand runs left to right in order, but bounces up and down between suits. This is the exact opposite character of the flush. In a flush, the row was fixed, and the columns were free. In a straight, the columns are fixed into a consecutive window, and the rows are free. Let us look at 3 examples to feel this contrast clearly. The first example is an ace-high straight. The 5 consecutive columns are 10, Jack, Queen, King, and Ace, the highest possible straight window. But now look at which box is highlighted in each column. The 10 column has the spades row highlighted. The Jack column has the hearts row highlighted. The Queen column has the diamonds row highlighted. The King column has the clubs row highlighted. And the Ace column has the spades row highlighted again. 5 consecutive columns, 10 of spades, Jack of hearts, Queen of diamonds, King of clubs, Ace of spades. The ranks are in perfect order, but the suits are all over the place. The second example is an 8-high straight. The 5 consecutive columns are 4, 5, 6, 7, and 8. The highlighted boxes are the 4 of hearts, the 5 of diamonds, the 6 of spades, the 7 of clubs, and the 8 of hearts. 5 ranks in perfect consecutive order, 5 different rows visited in no particular pattern. The third example is a Jack-high straight. The 5 consecutive columns are 7, 8, 9, 10, and Jack. The highlighted boxes are the 7 of diamonds, the 8 of clubs, the 9 of spades, the 10 of hearts, and the Jack of diamonds. Again, consecutive columns, scattered rows. In every straight, the column window is rigid and sequential, while the rows wander freely. That combination of column order and row freedom is the defining character of this hand. Now let us build the formula. And just as with the flush, we are going to use subtraction to make sure we do not accidentally include hands that belong to a different category. We write the formula as 10 multiplied by the quantity 4 to the 5th power, minus 4. Let us unpack each piece. The 10 counts the number of valid sequential windows of 5 consecutive columns in a 13-rank deck. We have established this number before. There are exactly 10 such windows, from the ace-low 5-high sequence all the way up to the 10 through ace royal sequence. 4 to the 5th power counts the number of ways to assign a row to each of the 5 columns. For each column in our chosen window, we can place the dot in any of the 4 rows, any of the 4 suits. And since each column makes its row choice independently, we multiply 4 by itself 5 times. 4 to the 5th power equals 1024. This counts every possible combination of suit assignments across the 5 consecutive columns. But here is the problem. Among those 1024 combinations, 4 of them happen to place all 5 dots in the exact same row. Those 4 combinations, 1 for each suit, are straight flushes. They meet both the sequence condition and the suit condition simultaneously. We have already counted them in the straight flush category, and we absolutely must not count them again here. So we subtract 4. 1024 minus 4 equals 1020. Now we multiply 10 sequential windows multiplied by 1020 valid suit combinations per window equals 10,200. There are exactly 10,200 straight hands in the deck. Notice the beautiful symmetry with what we did for the flush calculation. For the flush, we fixed the row and subtracted the sequential column combinations. For the straight, we fixed the column window and subtracted the uniform row combinations. Both calculations use the same subtractive logic. Include everything that satisfies your primary condition, then remove the overlap with the other condition. We have now accounted for 3 of the 4 cases in set D sequential and uniform, the straight flush, non-sequential but uniform, the flush, sequential but non-uniform, the straight. And now we arrive at the 4th and final case, the hand where neither condition is met. The columns are not consecutive. The dots are not all in the same row. No sequence, no uniform suit, no special pattern of any kind. This hand is the high card. In the grid, a high card hand looks wonderfully disorganized compared to everything we have seen before. 5 columns are highlighted, but they are not consecutive. There are gaps between them when you scan left to right across the ranks. And the 5 dots sit in different rows. No 2 adjacent columns share the same row, and there is certainly no single row that contains all 5 dots. The hand is scattered both horizontally in terms of which columns are chosen, and vertically in terms of which row each dot occupies. Nothing lines up, nothing runs in order. It is the most unconstrained, most irregular-looking hand in the entire deck. And yet, despite looking so chaotic, the high card is by far the most numerous hand type. Because it is the most free, the fewest restrictions, it has the most room to spread out across the 2.5 million possible hands. Let us look at 3 examples to see what this scattered, structureless pattern looks like concretely. The first example is a king-high hand. The 5 highlighted columns are king, jack, 8, 6, and 2. Look at those column choices. King, jack, 8, 6, 2. There are gaps everywhere. From king to jack, you skip a column. From jack to 8, you skip 2 columns. From 8 to 6, you skip a column. From 6 to 2, you skip 3 columns. Definitely not consecutive. And the highlighted boxes are the king of spades, the jack of hearts, the 8 of diamonds, the 6 of clubs, and the 2 of spades. The rows jump around with no pattern. Spades, hearts, diamonds, clubs, spades. No single row contains more than 1 dot. The second example is an ace-high hand. The 5 highlighted columns are ace, queen, 9, 5, and 3. Ace to queen, a gap. Queen to 9, a gap. 9 to 5, multiple gaps. 5 to 3, a gap. Clearly non-sequential. And the rows are the ace of hearts, the queen of diamonds, the 9 of clubs, the 5 of spades, and the 3 of hearts. The rows vary throughout hearts, diamonds, clubs, spades, hearts, with no uniformity. The third example is a 9-high hand. The 5 highlighted columns are 9, 7, 6, 4, and 2. The rows are the 9 of diamonds, the 7 of clubs, the 6 of spades, the 4 of hearts, and the 2 of diamonds. Non-consecutive columns, non-uniform rows. A classic high card hand. Notice something important about that third example. The highest card in the hand is only a 9. That means every card in this hand, 9, 7, 6, 4, 2, is lower than a 10. This is a genuinely weak hand. And yet it is still a valid poker hand, and there are many combinations like it buried within the enormous high card count. Now let us build the formula. This is the complement of everything we have already counted, and it uses the same subtractive logic we have been applying throughout set D. We write the formula as the quantity 13 choose 5 minus 10, multiplied by the quantity 4 to the 5th power minus 4. Let us unpack each part. 13 choose 5 counts every possible way to choose 5 distinct columns from 13. 13 choose 5 equals 1,287. This includes every combination, sequential and non-sequential alike. We subtract 10 to remove the sequential windows. 1,287 minus 10 equals 1,277. This gives us only the non-sequential 5-column combinations, the ones that cannot form any kind of straight. Then 4 to the 5th power counts every possible way to assign a row to each of the 5 chosen columns. 4 to the 5th power equals 1,024. This includes all row assignments, uniform and non-uniform alike. We subtract 4 to remove the cases where all 5 dots land in the same row, the 4 uniform suit assignments that would produce a flush. 1,024 minus 4 equals 1,020. This gives us only the non-uniform row assignments, the ones where the dots are scattered across different rows. Now we multiply the two parts together. 1,277 multiplied by 1,020 equals 1,302,540. There are exactly 1,302,540 high card hands in the deck. That number is staggering compared to everything else we have counted. More than 1 million hands, out of 2,598,960 total, are high card hands. Roughly half of all possible 5-card hands have no pattern whatsoever. They are just 5 mismatched cards that happen to be drawn together. And the formula reveals exactly why. When you remove only 10 sequential windows and only 4 uniform row assignments from an otherwise enormous space of possibilities, you are barely making a dent. The vast majority of column and row combinations produce neither a straight nor a flush. They just produce noise. Beautiful, abundant, structureless noise. Let us now take a step back and look at the complete picture. We have worked through every single partition, every single hand type, one by one, from first principles. And I want to bring everything together in one organized summary so you can see the full architecture of what we have built. We divided all hands into two master families, Set M and Set D. Let us revisit them in order. Set M covered all the partitions involving repeated ranks. The partition of 5 as a single group of 5 gave us 5 of a kind. The total was 0, impossible in a standard deck. The partition 4 plus 1 gave us 4 of a kind. The total was 624. The partition 3 plus 2 gave us full house. The total was 3,744. The partition 3 plus 1 gave us 3 of a kind. The total was 54,912. The partition 2 plus 1 gave us 2 pair. The total was 123,552. And the partition 2 plus 1 gave us 1 pair. The total was 1,098,240. Set D covered the single partition of 1 plus 1 plus 1 plus 1 plus 1, all distinct ranks. But within Set D, we further divided hands by two conditions, whether the columns are sequential and whether the rows are uniform. This gave us 4 subtypes. Where both conditions are met, sequential columns and uniform row, we have straight flush. This breaks into royal flush with exactly 4 hands and non-royal straight flush with exactly 36 hands. Together, the straight flush total is 40. Where only the suit condition is met, non-sequential columns, uniform row, we have flush. The total is 5,108. Where only the sequence condition is met, sequential columns, non-uniform rows, we have straight. The total is 10,200. And where neither condition is met, non-sequential columns, non-uniform rows, we have high card. The total is 1,302,540. Every single hand in a standard deck of 52 cards falls into exactly one of these categories. No hand is counted twice. No hand is left out. The categories are exhaustive and mutually exclusive. A perfect mathematical partition of the entire space of 5-card hands. And now, the moment everything has been building toward. The grand total. Let us add up every number we have derived, one by one, and see if they sum to exactly 52. Choose 5. 5 of a kind contributes 0. 4 of a kind contributes 624. Full house contributes 3,744. 3 of a kind contributes 54,912. 2 pair contributes 123,552. 1 pair contributes 1,098,240. High card contributes 1,302,540. Flush contributes 5,108. Straight contributes 10,200. Non-royal straight flush contributes 36. Royal flush contributes 4. Now let us add all of these together. 0 plus 624 plus 3,744 plus 54,912 plus 123,552 plus 1,098,240 plus 1,302,540 plus 5,108 plus 10,200 plus 36 plus 4. The total is 2,598,960. And 52. Choose 5. The total number of ways to choose any 5 cards from a deck of 52 is also exactly 2,598,960. They match perfectly, not approximately, not almost, exactly. Every single hand we counted, using every formula we derived from the structure of the grid, adds up to the precise total we calculated at the very beginning of this journey. The mathematics is complete, consistent, and airtight. This is what it means to partition a set. We took the universal set of all 5-card hands, divided it into non-overlapping families based on the integer partitions of 5, derived a counting formula for each family from first principles, and confirmed that the pieces reassemble perfectly into the whole. Nothing was assumed. Nothing was looked up. Everything was derived. And finally, let us close with a visual sense of just how dramatically different these hand frequencies are from one another. We have a chart displaying all 10 hand types, from high card on the left down to royal flush on the right, plotted on what is called a logarithmic scale. On a logarithmic scale, each step upward on the vertical axis does not represent adding a fixed amount. It represents multiplying by a fixed amount, specifically by 10. So a value at the second grid line is 10 times larger than a value at the first, a value at the third is 10 times larger than that, and so on. We use a logarithmic scale here because the raw counts are so wildly different in magnitude that a regular scale would be useless. High card has over 1 million hands. Royal flush has 4. If you tried to plot both of those on a regular scale where royal flush was even visible, high card would shoot off the chart entirely. The logarithmic scale compresses the enormous range into something we can actually see and compare. Let us read through the values from left to right, from the most common hand to the rarest. High card sits at the far left with a logarithmic value of approximately 6.11, meaning the count is close to 10 to the power of 6.11, which corresponds to our 1,302,540 hands. One pair is next, sitting at approximately 6.04, just slightly below high card on the chart, though still over 1 million hands. Two pair drops noticeably, sitting at approximately 5.09, corresponding to 123,552 hands. Three of a kind is next at approximately 4.74, corresponding to 54,912 hands. Straight sits at approximately 4.01, corresponding to 10,200 hands. Flush sits just below that at approximately 3.71, corresponding to 5,108 hands. Full house is next at approximately 3.57, corresponding to 3,744 hands. Four of a kind drops significantly to approximately 2.8, corresponding to 624 hands. Straight flush falls further to approximately 1.56, corresponding to 40 hands total. And royal flush, sitting at the far right at the very bottom of the chart, registers at approximately 0.6, corresponding to just 4 hands. Look at the shape of this chart and let it settle in. From left to right, the bars drop steadily and then plunge dramatically. High card and one pair tower over everything else. Then there is a significant step down to two pair and three of a kind. Another step down to straights and flushes. Another to full house and four of a kind. And then the chart falls off a cliff at straight flush and royal flush. Hands so rare they barely register even on a logarithmic scale. This is the full mathematical landscape of poker. Every hand type, every count, every probability, all of it flowing naturally and inevitably from a single idea. 52 cards arranged in a 13 by 4 grid, and the 7 ways to write the number 5 as a sum of positive integers. That is the math behind the cards. Thanks for watching, and I'll see you in the next video. Please consider liking, sharing, and subscribing to join our gentle community, and I would truly love to hear your wonderful thoughts in the comments below.